Hello. In this video, I would like to explain a step-by-step mathematical model derivation of stirred tank blending system. The objective of this step-by-step unsteady-state mathematical model development is to demonstrate a white box method in order to produce an unsteady-state transfer function which will represent the dynamic of a process control system, in this case a stirred tank blending process. If we look at the illustration on the right, we can see that the tank consists of two inlets and one outlet. Assume inlet 1 pore varies mass fraction of x1 and inlet 2 pore a constant mass fraction of x2. The unsteady state model will allow us to analyze the more general situation where process variables vary with time and accumulation terms must be included. Look again at the figure on your right, which is the isothermal stirred tank blending system. The volume of the liquid in the tank, which is denoted by letter V, can vary with time, and exit flow rate is not necessarily equal to the sum of the inlet flow rates, which is inlet 1 and inlet 2. Again, I would like to re-emphasize that the focus of this derivation is to derive unsteady state transfer function in term of ratio of the mass fraction of x over mass fraction of x1. Now, consider conservation of mass. Rate of accumulation of mass in the tank is equal to rate of mass for both inlets minus the rate of mass on the outlet. Note that there are two inlets which are inlet 1 and inlet 2. Mass of liquid in tank can be expressed as the product of the liquid volume, denoted by letter V, and the density of the liquid in the tank, given by ρ. In mathematical expression, mass of the liquid mixture in the tank, which is m, is given by liquid's density times volume of the liquid. Consequently, the rate of mass accumulation is simply dV ρ over dt, and equation 1 can be written as dV ρ over dt is equal to W1 plus W2 minus W, whereby W1 and W2 are mass flow rate for inlet 1 and inlet 2 respectively, and W is mass flow rate for outlet. So far, we have to assume that the blending tank is perfectly mixed. For perfect mixing assumption, the rate of accumulation of blending component A is dV ρ x over dt, where x is the mass fraction of liquid mixture A. The unsteady state component balance is given as dV ρ x over dt equal to W1x1 plus W2x2 minus Wx. Now we have equation 2 and equation 3 which show mass balance and component balance equation respectively. The dynamic model for stirred tank blending process can be derived from equation 2 and equation 3. Our ultimate objective is to get an equation, which is mathematical model, which is in appropriate form for computer simulation software such as MATLAB or Simulink. Assume constant density ρ for the stirred tank blending. Equation 2 and equation 3 become ρ dV over dt equal to W1 plus W2 minus W and ρ dVx over dt equal to W1 by 1 plus W2 by 2 minus Wx. Expanding equation 5 using product rule gives ρ dV over dt equal to ρ v dx over dt plus ρ x dV over dt. Substitute equation 6 in equation 5 gives ρ v dx over dt plus ρ x dV over dt equal to W1 by 1 plus W2 by 2 minus Wx. Substitute mass balance in equation 4 for ρ dV over dt term in equation 7 gives ρ v dx over dt plus x times W1 plus W2 minus W equal to W1x1 plus W2x2 minus Wx. Rearranging equation 4 in term of dV over dt gives dV over dt equal to 1 over ρ times W1 plus W2 minus W. Rearranging equation 8 in term of dx over dt gives dx over dt equal to W1x1 plus W2x2 minus Wx minus x times W1 plus W2 minus W over ρ v. Cancelling common terms resulting dx over dt equal to W1 times x1 minus x plus W2 times x2 minus x over ρ v. Now we have two equations, which are equation 9 and equation 10, which are written in more convenient model form. This form is also called as state space. We will cover about state space in different lesson. This mathematic expressions is valid for liquid volume V is constant, which is dV over dt equal to 0 and exit flow rate is equal to sum of inlet's flow rate. Next, we are going to derive transfer function. To derive transfer function, several assumptions have to be made. First, ρ and V are constant. Second, W1, W2 and W are also constant. And third assumption is x1 is varies and x2 is constant. Using first assumption, which is ρ and V are constant, rewriting equation 3 gives ρ v dx over dt equal to W1x1 plus W2x2 minus Wx. The steady-state version of equation 11 is 0 equal to W1x1 bar plus W2x2 minus Wx bar, where the bar over a symbol denotes a nominal steady-state value. Subtract equation 12 from equation 11 results rho v dx over dt equal to W1x1 prime minus Wx prime. Note that x1 prime is approximation of x1 minus x1 bar and x prime is approximation of x minus x bar. Because x bar is constant, it follows that dx over dt equal to differentiation of x minus x bar, which is dx prime over dt. Substitute equation 15 in equation 13, resulting rho v equal to W1x1 prime minus Wx prime. Applying Laplace transform on equation 16 yield equation 17. Rearranging equation 17 to get equation 18. Divide right-hand side of equation 18 with term W, resulting the final transfer function which represent the stirred blending tank process. This transfer function provide the ratio between system output and the provided input with K1 as the process gain and tau as the time constant. It is clear that the white box derivation provided first-order system. As a conclusion, constructing mathematical model using white boxes requires complete mechanistic model is constructed from a priori knowledge and physical insight. The dynamic models are derived based on mass, energy, and momentum balances of the process. A slight mistakes may result in accurate dynamic model. That's all. Thanks for watching.